We get started. Okay, those on the internet, can you hear me? Okay, let's get started. This tutorial, question 1. Any questions on number 1? No. So again, the same question would be how to get started. Does everyone know how to get started? Any questions of how to get started on this tutorial, question 1? Anyone want me to discuss question 1? Hands up, please. Yes. Okay. How do we get started? Those on the internet also, please suggest how you get started. Huh? Draw. Okay. So draw something. What are you going to draw? What are you going to draw? Yeah, please. What are you going to draw? Magnetic field. Okay. So maybe we should ask ourselves, what do we hope to see from that figure that we draw when we draw the magnetic field? Okay, so maybe when you draw, are you drawing magnetic field or are you drawing magnetic flux density? Do you want to draw magnetic field or you want to draw magnetic flux density? Any difference or not? No difference, right? The visualization, no difference. But calculation there is, right? Because magnetic flux density depends on the medium, right? Because it's mu times h, right? B is equal to mu times h. So strictly in quantification, you need to know whether it's embedded in some medium that will increase the magnetic flux density for a given magnetic field. Okay, so when we draw that, we actually have this picture here, right? I mean, okay, so that's the B. The B is given to you as minus AZ. So what does it mean when it says minus AZ? So what do you draw? What do you draw? So your starting point is always draw the three axes, right? The three axes, X, Y, Z, right? So do you want to draw a 3D XYZ or you want to draw a 2D XYZ? Your choice. Do you want to draw a 3D XYZ or 2D? 2D. Okay. So if you draw 2D, you need to choose two axes to draw that plane, right? Two axes form a plane. So you have X, Y, and Z. Which two are you going to choose to draw? X, Y. Why? 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 Sorry. Why again? Yeah. Please. Yeah. Why do you want to draw XY plane? Why not XZ plane? Why not YZ plane? Three choices, right? Huh? Because they draw for you already. Okay. I mean, okay, they draw for you like that, but let's say you're just given a question, you are going to draw it yourself, or you think, would you draw a different figure from what they draw? Would you choose instead of XY plane, XZ plane, or YZ plane? Would you choose that? Would that be better? What do you think? What do you think? Huh? If you, let's say, okay, this is given to you in XY plane, right? If you are going to draw exact plane, does it help you? No. Why it doesn't help you? Why it doesn't help you? If, by the way, those of you who don't know how to get started, you have to think about this question seriously, because it is, you need to know what are you visualizing. Because if you don't know what you're visualizing, it doesn't help you in drawing. So what do you want to visualize? Do you want to visualize magnetic flux, or do you want to visualize magnetic field, or do you want to visualize magnetic flux density? Which one do you want to visualize? What's the difference between the three? Okay, I just discussed the difference between magnetic flux density and magnetic field, right? We say magnetic flux density B is mu times H, right? So whether you visualize magnetic flux density or magnetic field is similar. That's the difference by mu, which is basically stating what kind of material that medium is. Now, magnetic flux. What is magnetic flux? What's magnetic flux? It is magnetic flux density multiplied by area. Multiplied by area. Okay, so that's a keyword, right? So when you visualize, if you want to visualize magnetic flux rather than magnetic flux density, you have to think about the area. You need to visualize the area. Okay. So now with that in mind, do you want to draw XY plane, XZ plane, Y plane? I mean, YZ plane? Which one? XY, right? Because the area is in XY plane, right? Area is in XY plane. Okay, so that's why we want to visualize XY plane. Okay, so we have chosen x-axis, we have chosen y-axis. How do you want to draw this? I can draw x like in this figure, that means going towards my right. Y like that. Can I draw x going left and y going up? Yes, right. Your choice, up to you. You draw. You draw. Yeah, okay. This is one of the conventions. But if you decide to be different, I like people to be different. That's perfectly fine. So likewise, I say, you want your positive x in the left or the right, it's your choice. You want your y top to be positive or bottom positive is your choice. After you have drawn it, your z positive direction is fixed by your right hand rule. Okay, after you have defined, after you have drawn which direction is your x-axis positive, which direction is your y-axis positive, then your z-axis is defined by your right hand rule. So in this case, if your x-axis is like this towards your right, your y is towards the top, by right hand rule, it is coming out of the paper, right? Coming out of the paper, right? But if you decide to change it and say, okay, your y-axis is going downwards, positive, then it's going into the paper, right? Z-axis, right? Okay, so it's important for you to label, okay? It's important for you to label. This is incomplete, huh? This is incomplete. You need to label where is the positive z-axis. Understand it? This is not complete. Huh? You need to label. That means you need to draw a circle. Is that circle with a dot or with a cross for positive z-axis? Dot, right? Because it's coming out, right? Coming out of the paper. Okay, so we should strictly draw here now. Anyway, okay, you can draw it at the origin with a dot and say that's the z-axis, or somewhere here with a circle with a dot and that's the z-axis. Okay, telling you that coming, the z-axis is perpendicular to this white paper, is coming out for positive z. After you have done that, now you can visualize in this 2D plane the magnetic flux density B, because the magnetic flux density B is given as minus AZ. So in other words, they are basically cross, right? Circle with a cross, right? Yeah, so saying that it's going into the white paper, right? Okay, so that's why we draw all this round with cross and say that that's your B vector, your B vector. That's the magnetic flux density. Yeah. That will capture this minus AZ direction. Okay, and it has an amplitude of 0.3 T. T is the time, of course. This capital T is Tesla. That's the unit. Yeah. Okay. So next thing, as we said, we need to visualize the flux, right? Magnetic flux. What's magnetic flux? Why we need to visualize the magnetic flux is because ultimately we want to calculate the voltage V1 and V2, right? Here in this circuit. So we need to visualize the magnetic flux. Why? You need to basically apply Faraday's law, right? So what is Faraday's law? You can get it from your exam appendix. Which of this equation is Faraday's law? Or indirectly, I'm asking you is, which of this equation do you want to use to find your answer for this question? The last one, right? This is basically your Faraday's law, right? Okay, this one. Okay. As it says, the EMF in the middle, right? Can you tell me in your own words what is the, okay, let's start from right hand side. What is the right hand side here? What's this? What is this in words? What does this calculate? Yeah, this is calculating the total magnetic flux, starting from a vector dot product of B and ds, right? B is a magnetic flux density, is a vector. ds is another vector. ds is the small area vector. So flux density times area give you magnetic flux, right? This is the magnetic flux, but over a small area. So when you double integrate, you get the total flux. Next, you find how it changes with time, right? d dt. So, and put the negative, that's your Lenz law. That is basically your EMF induced. Why is there EMF induced? It's because, you know, this time varying flux creates a curl of E. It creates a curl E, basically. The E field curling around the circuit in your DL path cross loop. That is basically your voltage, right? E dot DL is voltage, right? Remember? So that actually creates this EMF once you form the full loop, full loop around it. Okay, so remember this EMF, the voltage created is due to time varying flux. It's due to time varying flux. It's like a battery in your circuit that is created because of time varying flux. Okay, so now we're going to use the equation to solve. Okay, so let me show you my solving. Okay. So our starting point is calculating flux, right? Our starting point is calculating flux, which is magnetic flux density times area. So now the question is, do you want us to start from a small area, or you just multiply by the total area? Rather than do a double integral, you just straight away multiply by the total area. Exactly. Okay, that's the point. You need to look at your B because you're going to do a magnetic flux density times area. So you must make sure that that area has an uniform magnetic field, right? Magnetic field density, right? So you can see that the B is independent of X, independent of Y, meaning it's uniform in X direction, uniform in Y direction. So hence, even if you do a double integral, you still get the total area, right? S, right? Which is 4 meters square given to you, right? Okay, next thing is, remember the area is a vector, right? So where is the direction of that area vector? So it be negative AZ or positive AZ? All agree is AZ, right? Because it must be perpendicular to the area, right? So perpendicular to this area, which is in the XY plane, means is parallel to the Z-axis. Is it positive Z or negative Z direction? How do you determine? Okay, so follow this rule, which will capture Lenz law. Follow this rule. First, you label the current flow in the loop. You do that first, okay? Label the current flow in the loop. So in my case, I decide to label the current flow in anti-clockwise direction. That's just my choice. If you want to choose it to flow clockwise, also perfectly fine. You must choose first, okay? After you have chosen, use your right hand grip. The fingers follow the direction of the arrow, the current, direction of the current. Your thumb is the direction of the area. So if I draw my current anti-clockwise in this case, you can see my thumb is coming out of the paper. It's positive AZ. If I change the loop current direction to be clockwise, then I have negative AZ. Okay, so make sure you do that first. In your figure, label your current direction, the loop current direction. Label it. Okay, so since I label it anticlockwise in this case, that's why my area is positive AZ. So hence now I have my total flux is just my B times my area, and the vector dot is AZ dot AZ, right? So it's 1, right? And this negative sign remains. So therefore I have minus 1.2 T, right? When I multiply the B of 0.3 T with a negative and the area of 4, right? Okay, next, I need to find out how this total flux change with time by differentiating it with time, right? So obviously this easy differentiation is 1.2, right? With a negative. But there's another negative here in the equation. So that gives me a positive EMF voltage of 1.2 volts. Meaning the current is indeed flowing in the anti-clockwise direction. Had I labeled it the other way around, I will end up here with a negative value, meaning the current is in the opposite of whatever I labeled. Now you can go and test Lenz's law. The current is indeed flowing in this way. Does it satisfy Lenz's law? The induced current is flowing that direction, right? Does it satisfy Lenz's law? Yes, right? Because you go like that, if the current flow like that, inside the loop here, inside the loop, the magnetic field is coming out of the paper, right? So it's opposing the B, right? So indeed, you can verify it satisfies Lenz's law in your calculation. Okay, so that's done for EMF. So next you're going to calculate is, what are you going to calculate next once you know EMF? What do you think? What are you going to calculate next? Well, we just already calculated the induced voltage, right? The EMF is 1.2 volts, right? What's next? Induced current. Okay. How are you going to calculate the induced current? Okay, so what you're going to do is you just go and visualize. I think many of you are from Polytechnic, so you used to be very strong in circuit theory, right? So you go and visualize this circuit here, insert that EMF as a battery in the circuit. Okay, so I'm going to insert it somewhere, let's say here. I'm going to black this circuit here, right? This wire here, and insert the battery. The battery has a positive and a negative. So it be positive, then negative in series here, or negative and then positive in series. Which way? Well, I label the current this way, right? That implies the battery is pushing out with positive, right? So that means, whatever the arrow go in should be the negative of the battery, right? And then the positive is pushing the current out, right? Okay, so just remember, when you put this battery, you have a negative on this side and then positive on the other side, right? Pushing the current around like that. Remember, the current flows out of the positive terminal of the battery, coming back into the negative of the terminal of the battery. So just do that. You insert that battery in there, then I'm sure you know how to calculate I. If you don't do that, you just look at that, you will wonder how to calculate. What is causing the I to flow? No battery, right? Yeah. Okay, so with that, all of you agree the current will be just 1.2 divided by total resistance of 6 ohm, right? So hence the current is 0.2 ampere, right? So what's V1 equal to? What's the voltage across these two resistors? Potential divider rule or Ohm's law? Ohm's law, right? V equal to IR, right? Okay, notice whenever you measure voltage using a voltmeter, there's a positive terminal, there's a negative terminal, right? So this is labeled that way, okay? You want the positive terminal on this side, the negative terminal on that side. So this voltage that you measure, is it positive voltage or negative voltage? Should be positive, right? Because our current is indeed flowing this way, right? So it's pushing into the 2 ohm through here, right? Which makes this positive and that negative, right? So you should get a positive value for your V1. which is equal to 0.2 times 2, right? Yeah, so you get positive 0.4 volts. So same thing over here, right? Yeah, the current is flowing in here, 0.2 times 4, give you 0.8 volts, right? Oh, okay with that? Okay, now it comes quiz question. And this may indeed be your quiz 1 question. If I replace this 4 ohm resistor using a voltmeter, I put a voltmeter here. Can you tell me the voltage that you will measure across V2? 1.2 volts? All agree 1.2 volts? What will be the voltage across here, V1? Okay, 0 volts. All agree with that? Any of you cannot see that? Why? What's the resistance of a voltmeter? Yeah, very, very big. Yeah. Yeah. So practically most of them will be mega ohm lah. Yeah, in the order of mega ohm. Okay, next. What if I replace it by an ammeter? Put an ammeter here in place of this 4 ohm resistor. What would the ammeter read? Yeah, your original 1.2 volts battery divided by now only 2 ohm, right? Because ammeter is a short circuit, right? So therefore you will read 0.6 ampere of current, right? And this one will read, what voltage will this read? Yeah, this will read 1.2 volts. Okay, what if I change this 4 ohm resistor into an inductor of 1 millihenry? Inductor of 1 millihenry. Please discuss those on the internet. There are a number of you there. I would like to see some response, some participation. If we replace the 4 ohm resistor with an inductor of 1 millihenry, what will be V2? What will be V1? Okay, so please tell me what goes in your head. How to evaluate the current first, right? You need to evaluate the current first, right? Same as before. Your EMF don't change, right? Still 1.2 volts, right? Yeah. So what do you do with the inductor? Short circuit. Yeah. Okay. Why short circuit? Because it's DC. The EMF is DC. You have to look at your EMF. Okay. So EMF at the end of the day is 1.2 volts, right? Yeah. The EMF is 1.2 volts. There's no sinusoidal term at the back. Had your B been some sinusoidal wave, then your EMF will end up with some sinusoidal term at the back, right? Like your latter question. If that is the case, then you have to use J omega L, right? Remember, the reactance of the inductor is J omega L. Omega equal to 2 pi f, right? Whatever frequency that sine wave is at. Okay. But in this case, your EMF is DC, hence it's 0 ohm. Okay. Yeah. So if it's 0 ohm, V2 will be 0, similar to like when we use an ammeter, right? Yeah. What if you change this 4 ohm resistor to capacitor of 1 microfarad? Yeah, capacitor, again, DC is open circuit. If it's a sinusoidal wave for your EMF at some frequency, F, cannot say short, the reactance of a capacitor equal to 1 over J omega C, right? Yeah, so it depends on your omega and your C value. Yeah, may not be short. Yeah. Okay, so just take note of that because the quiz may ask you these things, although it's not taught as such in this course itself. These are like assume that you should know on the circuit theory. You look puzzled. Of course, you are seem to know already. You're not third year, you know. You already covered all this in your second year. Yeah. Question 2. This is your second question. Huh? So what is here? You have two wires. First wire is located at x value of 0, running in parallel to the z-axis in the positive AZ direction for the current. And then the second wire is running at x equal to minus a, parallel to the z-axis with a negative AZ direction current. Okay, so obviously because you pass some current through these two wires, they generate a magnetic field, right? That result in some magnetic flux density in this loop, right? And hence magnetic flux in this loop, right? So if there's time varying flux, there will be induced current. Is there time varying flux in this case? No, it's moving. Yeah, it's this wire loop is moving at constant velocity. So what happens? Well, so we remember that flux, magnetic flux equal to magnetic flux density multiplied by area, right? So is the area changing with time? No. Is the magnetic flux density changing with time? Yes. Why? Why? Why is the magnetic flux density changing with time? Exactly, yeah. So magnetic flux density is proportional to the distance, the radial distance from the line, right? The wire that has the current, right? So this loop, if it's moving, the radial distance keep changing with time, right? Okay, so that's the reason why it creates that time varying flux. Right? Okay, so by that we have already captured, you know what we need to do to quantify it. Okay, that qualitative description, you know, captures what we need to do. So what's the first thing we need to do in order to calculate the induced EMF in the loop? What's the first thing we need to do? We need to go and calculate what's the magnetic field due to the wire, right? Due to the I naught flowing in those two wires, right? So how do we do that? Yeah, we draw the diagram. Okay, now which diagram do we draw? Okay, so Wei Zhang, you mentioned use superposition theory. Okay, so that means by that I believe what you're saying is that since there are two wires, let's use one, find the magnetic field, find the magnetic field for one wire at a time, right? So let's say we start with the first wire here. Okay, this wire at x equals 0. So we don't care about this wire for the time being. Huh? We start with this wire. What's next? Remember, we want the magnetic flux density, right? So you must visualize magnetic field in the way that eventually you can get your result and also the flux, right? The magnetic flux, which is the area, right? But right now, our concern is to find the magnetic flux density. Agree? That's what we need to do now, right? We need to find magnetic flux density. So what do you want to visualize to find this magnetic flux density? What do you need to visualize? You need to visualize magnetic field, right? So to visualize magnetic field, what are you going to draw? Yes, exactly. You're going to draw the XY plane, right? You're going to draw the XY plane because the magnetic field is going to go round and round the XY plane. Agree? Go around the XY plane. Okay. I'm lazy. I'm not going to draw it. Okay. So you have to draw it in your head. Draw it in your head. Okay. So that circle that you are drawing in your head in the XY plane has a center at the center of that wire, right? Which is x equal to 0, y equal to 0. At which z value? So if it's z equal to 0, z equal to some other value. At z equal to 0? Agree? Okay, so we are going to draw that circle, okay, in our head. X equal to 0, x value is some positive x value, right? Y equal to 0, z equal to 0 is that circle that we visualize, right? It's going to pass through this point at some x value in the xy plane. Huh? Okay. So that magnetic flux density has some, or that magnetic field has some direction and some magnitude part. What is the direction of that magnetic field? Yeah, point into this white paper, right? And we label, in this paper, we label this is X, this is Z. So where is Y-axis? Where is positive Y-axis? Into the paper or out of the paper? Into the paper. How do you get this answer? Right hand rule. Or you can use what you want Y, right? So Z cross X, right? AZ cross AX. Yeah, AZ cross AX give you AY. Okay, so all agree by that we have the AY direction is going into the white paper. Okay, so now we already got our direction for our magnetic field. How about the magnitude? How do you get the magnitude part? So you need to apply Ampere's law, right? So you visualize in your XY plane is a circle in the XY plane, right? So the radial distance of that circle is X. So the circumference length is 2 pi X. And it encloses a current of I naught, right? So therefore, that H magnitude is equal to I naught divided by 2 pi X, right? All agree with that? Okay, so that's the magnetic field that we have already calculated due to this first wire. Okay, so very quickly you can get the second wire, right? What's the direction of the second wire at the same field point, that X value, X00? It's opposite direction now, right? Just now was positive AY, now it's minus AY, right? What's the scalar part, the magnitude? So again, it's a concentric circle now, but it's centered at X equal to minus A, right? So the total radial distance is now X plus A. So circumference length is by X plus A, right? Okay, so therefore we have the same I minus I naught AY divided by 2 pi X plus A, right? Okay, so that's how we get the total magnetic field. Okay, this is the first one now. I want the second one. Okay, so this plus this, right? Okay, so this terms here, right? And then multiply by mu will give me flux density, right? So if it's free space, it's just mu naught, right? Mu r is equal to 1. Yeah, it's free space. Okay, so now we already have our magnetic flux density B at this point, right? At this field point. Yeah. Okay, so our next step will be to calculate the flux, right? Magnetic flux, which means we need to multiply by area. So you need to now go and ask yourself, are you going to use the total area or you're going to use a small area? Small area, you can see the area is in X and Z axis, right? So you're going to do a dx dz, means a small little area here, or you're going to form an entire column area like this, like what I've drawn here. Like this. Why?
This the line, the that evenly distribute the parts.
Yeah, exactly. So again, the same reasoning. You go and look back at your B, right? Your B is only dependent on X. It's independent on Z. So when you integrate with Z, you're just going to get the answer of the length, right? In Z, which is A, right? Yeah, so you might as well just consider the whole column length. Okay, so we use the Z length, which is A, and then the increment in the X, which is dx, right? At this point, right? So therefore, our ds vector is A dx, right? It's a scalar part. The direction, again, you have to label the current flow loop direction first, okay? So you have to label the current flow loop direction first. In this case, I decide to call it in the clockwise direction. That's for fun. You can say anti-clockwise if you want to, up to you, okay? So once I say is clockwise, again, I use my right hand grip. My fingers follow the current I. My thumb is the direction of the area. So it's going into the white paper, right? So meaning, is that positive AZ? AY? That's positive AY, right? Okay, so that's why my area is positive AY direction. Area is positive AY direction. Okay, next we're basically going to do the flux, magnetic flux, right? By multiplying the B vector with the DS vector, right? It's a vector dot product. So this might be, so I have AY, dot AY is 1, right? So hence I have all these terms multiplied by this ADX is my scalar term, right? In the flux. Then next, I need the total flux. So total flux says I need to integrate over dx, starting from my x value of this leftmost wire all the way to the rightmost wire, right? So at time 0, of course, it starts from A, x equal to A, and then end at 2A, right? But in general, we need it at any particular time. So therefore, this left wire will be at A plus V naught T, right? Because the whole thing is moving at V naught T. Okay, and then the ending of X will be 2A plus V naught T. So that's why my integration limit to get the total flux is integrating from A plus V naught T to 2A plus V naught T. Okay, so now for up to here, your formulation, if you get this right, everything else below this will be just maths. You need to know how to integrate 1 over x dx. What's the answer? Ln x, right? So this is no formula given to you. You assume you need to know this, one of the basic integral form. Integrate 1 over x dx equal to ln x. Can you prove it? I cannot remember how to prove it. Yeah. Okay, so this one same, right? Ln x plus a, right? Okay, so put in the limits, and this is it. Don't bother to simplify, okay? Don't need to simplify because later on you're going to differentiate anyway. Yeah, with time, okay? Okay, so after this, we're going to find d phi by dt, differentiate with time. Okay, so it's a straightforward differentiation, right? You integrate the term, you get what ln, right? You differentiate ln, you get 1 over the term. Right? Simple reverse solution. Okay, so eventually we get our EMF is negative, right? Meaning the current is not anti-clockwise. I mean, not clockwise, but rather in anti-clockwise, right? Does it agree with Lenz's law? Yeah, so because we found the current is actually negative. Yeah, EMF negative means current is negative, right? So the current should be going this way, right? Anti-clockwise. Huh? Is that correct? No? So you reason out with Lenz's law, right? That is, it should be indeed anti-clockwise. Any questions on this number 2?
Because the lens will go off.
You must oppose the movement. Yeah. One way is look at it, you must oppose the movement. Second one is you must oppose the decreasing in magnetic field strength, right? As you move further and further away, your magnetic flux density become lower and lower. You have to oppose that by trying to increase back. This question itself don't ask you that how you just say induced EMF. So in induced EMF, until you put a voltmeter with a direction labeled clearly, is arbitrary. Yeah, so that number 3, as it is induced EMF, you could have positive or a negative answer, doesn't matter. Unless we put a voltmeter in there, like this question. But this question also arbitrary because never label this is positive, this is negative, or this is negative, this is positive. If this is labeled, then it's very clear. Okay, so we come to question 3. Solve question 3. Okay, so question 3, you have, first of all, your magnetic flux density is time varying, is given as time varying according to a sinusoidal wave. Yeah, so it's 2 sine 20t. So this is your omega lah. Omega equal to 2 pi f, right? Which value is 20. So from there you can find the frequency. Its direction is positive AZ. So once we have identified that this is positive x-axis, this is positive y-axis, our Z would be coming out of the white paper, right? So hence a dot, right? So that's why we visualize the B with a dot like that. Right? Visualize the B with a dot. Just take note that although your B is sine, so we are just tracking the positive edge. Because remember, a sine of something, there's a positive cycle and there's a negative cycle, right? The negative cycle, the actually reverse the direction. Right? So we're only tracking the positive by the drawing. Okay, so next thing is we have this loop right here, right? This loop here, because all these are conducting wire, right? However, this loop area is changing with time, right? Because this bar here is moving at a velocity of 25 AX, meaning its area is increasing by 25 meter per second, right? This X value. So our magnetic flux is changing, time varying due to 2 things. B itself is changing with time, and the area is also changing with time. Yeah. So obviously, when we formulate, we're going to do the formulation that way, right? Okay. So remember, we're going to find the flux, right? Total flux. So total flux is flux density, which is this one, multiplied by your area. So again, are we going to use a small ds or the total area? Do you need to use a small area? So same question again, right? Is your B uniform in X and Y? If it's uniform in X and Y, there's no need. Just multiply by the area. It is uniform in X and Y, right? There's no dependency on X and Y for B. So just multiply by the total area. So what is the total area at time t? The Y length is 0.1, fixed, doesn't change with time. The X length is at time t, what's the X value? This one. 0.1 plus 25t, right? Okay, so that's your area, right? Okay, so that's why my answer here. Yeah, my answer here is this now. So here's our flux, right? Okay, same thing again, area direction. So where's the area direction? Label your current first. So in my case, I decide to flow the current in the anti-clockwise direction. So hence, by my right hand grip, my area direction is coming out of the whiteboard, which means it's positive AZ, right? So I have my area vector is positive AZ. So when I calculate the total flux, is this P dot this, right? So AZ dot AZ is 1. So scalar part is this 2 sine 20t multiplied by this area of holding here, right? So I get this. Okay, so next is just differentiate this, right, with time. So there are two time dependency terms, which means you need to keep one constant, differentiate the other, and then keep the second constant, differentiate this, right? So that's how I get this answer. And then the length law here with a minus in the here with this big square bracket out of it, right? Okay, so with that, that's our answer really, right? That's whatever simplification you want. Yeah. Okay, so like I said, now my EMF net result is a negative, yeah, meaning that my current is flowing this way, right? Clockwise direction. Satisfy Lenz's law? Yeah, right? Just look like that. We'll go in, right? Inside here. Any question, anyone on this? Any question? If not, then I want to use the remaining time to discuss with you your quiz one rather than our usual of discussing the lecture slides, because your quiz is coming out in next Saturday, not coming Saturday, but the following Saturday, right? Okay, first question is, do you know the topics that are covered? Okay, tutorial 1 to 5, meaning up to this tutorial questions. What is next tutorial? Obviously, is all waves, plane waves, something to do with plane or the waves, right? You can see next tutorial. Yeah, all the questions are on waves. I think there were some questions from someone. Yeah, you asked about what exactly are the slides you need to go through in your lecture slides. Okay, so let's go to tutorial 5. Lectures. So these are the week 5 lectures which you're supposed to have gone through. Let me just go through them. Displacement current, yes, is covered in the quiz. Any questions on displacement current? Although this happened to be a question in your next tutorial, but it is covered in your quiz. What is displacement current? What's conduction current first? What's the equation for conduction current? All of you downloaded your quiz cheat sheet? How many of you have not downloaded your quiz 1 cheat sheet? In other words, the formula sheet. Who Where is the formula sheet? Yeah, it's in your content. Now go and download it if you have not. Huh? So I'm going to open it up and show you.
We bring our own.
No, you're not allowed to bring anything. It will be given to you. Okay, this is a quiz one sheet. I don't see conduction current equation there. Wait. Now let me decrease the size of it. Oh, this one. Not quite. Huh? This one? Are you referring to this one? This one just says, okay, this is conduction current density. This is displacement current density. So the curl of H is the sum of the two. That means you could have a current of H due to a conduction current. That means conduction current density, or it can be displacement current density. That's what it's saying. My question to you is, how do you find conduction current density or conduction current? You need that equation. J is equal to sigma E. Sigma is conductivity. E is the electric field. J is a vector, right? J is a vector. E is a vector. So J is equal to sigma E. Sigma is conductivity. I don't see in this formula sheet, unfortunately. You need to memorize it, yeah. And then displacement current is okay. Displacement current, you can find it from this term. That means you need to, if you know the flux density, electric flux density, you differentiate with time, you get your displacement current density. How do you get your electric flux density? Well, if you know the electric field or some other method, right? Yeah, or you know, because you know the volume charge density. Okay, so what else in those lecture slides? Let me go back to the lecture slides. Just now I was in week 5, right? Okay, next one. Maxwell equations. Yes, you need to know all these Maxwell equations. They are given in there in the formula sheet. Next one. Phasor notation. Yes, you need all this also. Next one. Introduction to plane waves. I think this you don't need. Yeah, you don't need any of this. Next one. I think the rest all on plane wave, right? Am I right? Yeah, wave equation. Don't need this either. Yeah, okay. So as far as the week 5 lectures is basically the first two, we say, right? 14 dash something is on the, oh, 14-1 also you need. Is that clear? I think one of you, is that clear to you now? Okay. So like I said, very important, you download this formula sheet and learn how to use it, just like your exam appendix. Make sure you know how to use it. This one, compared to your exam appendix, These are constant values which are also given in the exam appendix. This one is not given in the exam appendix, but indirectly, this is Coulomb law. Force equal to charge times E field. This is your E field. This one also not in your exam appendix. This is saying the total force acted on some charge can be a combination of electric field and magnetic field. So it's the so-called Coulomb's force and the Lorentz force, right? Coulomb's force is the electric field part. Lorentz force is the magnetic field part, right? Or magnetic flux density. Next one, this one is familiar. It's in your exam appendix. This also in your exam appendix. This one. E is equal to the gradient of the voltage with negative. I can't remember whether it's inside your exam appendix. Is it? Maybe not. This is your exam appendix. I don't think it's there. It's not there. And then potential difference also not in your exam appendix. So potential difference is E. Actually, you can get it from the hint of the units. Electric field unit is watt per meter, right? So you must multiply by length to get volts, right? So that's why you multiply by length. You multiply by length. But in general, you multiply by small length so as to keep the E constant over that small length. If your E is uniform, then no, you must just multiply by the total length. This one is Biot-Savart's law given. This one is calculating total current, right? From current density times area, right? So it's equal to total current. And that is equal to this integration of H round the closed loop. This is Ampere's law, also given in your exam appendix. This one, we just use it in our tutorial here now, right? Okay, all these are Maxwell equation. These are all your vector manipulation, the gradient vector, the curve vector, the divergence of a vector. All these are what? All these are rectangular, no cylindrical given. Oh, interesting, no cylindrical given. So presumably the quiz don't have cylindrical. Is that true? Not true, you know. I've at least come across one question that is cylindrical. Okay, so next thing is any other question about the quiz? I think all of you know, must go to your NTU Learn TEL course. Under the TEL course, under content, right? At the back there, all this information are there. As to what is exactly your time, which session, I think you will be notified soon. How come now you still have not received it? Is it? You don't know yet, huh? Yeah. Off my head, I remember is somewhere between 10 to 12, 2 sessions. Yeah, because 45 minutes each session, right? There are 2 sessions, but there are many labs, because there are so many of you. So you need to check which lab you are. Okay, next. What kind of questions do you expect? You must go to your Oasis and learn now. So I'm going to walk you through Oasis. If you have not done it, follow what I'm going to do now. So open your web and go to Oasis. Anybody know how to get to Oasis? I always type the word practice first. Practice is the keyword. Then you come out .ntu.edu.sg/Oasis. Okay, log in. Okay, I've logged in. Choose my course. You don't need to do this. You're supposed to see this. Okay. So let me warn you. The quiz question is at least average, if not a little bit more difficult than average. So let's go straight into the average question. I'm not going to go through the easy question. Which topic do you want to start? Start with? Oh, I mean, we are going to go through the average. So which average? Okay, so the order, okay, up to which one you need to do? You need to go all the way up to Ampere's law here. P12E, P15, P16, these four, no need. They are plane wave, right? Up to 12E. Okay, so if you scan through the topics, I think our tutorial did not do any on Coulomb's law, did not do anything on Lorentz force and Gauss law, did not do much on electric potential. Okay, so we start from here, Coulomb's law average. Okay, view question. Okay, this question. Do you know how to solve this question? Two-point charge, 12 coulomb, 3 coulomb. So in other words, the 12 coulomb is located at x equal to 0, y equal to 0, z equal to 0. The 3 coulomb is located at this xyz location. A third charge of -1 coulomb is placed at some location such that the force is 0. Find that location. So in other words, remember force is equal to Q times E, right? Your Q is your -1 coulomb, right? Your E is the net E due to that two charge, which need to be 0, right? In order for your force to be 0. So you tell me, where should your electric field be? Which location for it to be 0? What do you think? Qualitatively first, where is it? Between those 2 points, right? Or where the two charges are, because both of them positive, right? So it's EV is radiating out, so they're pushing against each other. So you draw a radial distance between those 2 points. Okay, next, what goes on in your head? You start thinking about the E field strength, right? It's proportional to what? Proportional to charge. And 1 over distance square, right? Inversely distance square, right? So where should it be 0? Because the charge of 1 is 4 times the other. By how much exactly? It's 4. The charge is 4 times, so the distance must be 2 times. Okay, and then you have 1, right? So that total radial distance divided by 3. Yeah. And that 0 will be closer to the weaker charge. 1/3 from the weaker charge. Okay, so all picture that. If you picture that, you just need to draw that and work out from geometry. Next question. What is the total charge on this line? This one should be easier. All know what to do? Q is equal to integral rho L times dx, where x vary from
0 to 10.
0 to 10. Yeah, exactly. Okay. This one, rank the magnitude of force on P. P is this middle, okay? Middle point. You want the force. So basically, you need to know because there are 4 other charges, right? 2 from the left, 2 on the right. That's creating the E field that this charge experience, right? Every one of these, right? So you note that the distance to those on the left and the right, the first one is 1r, whereas the other one is 2r, right? So you just think of the force superimposed, you go and calculate. First of all, it's proportional to charge. But fortunately, all these are either plus Q or minus Q. Then next is distance square, right? Inverse distance square. Okay. But those are the rules in your head. To do some superposition, you can find out your answer. Okay with that? Two charge, Q1, Q2, placed at some distance d. The attractive electrostatic force between them is F. That means, basically these two charge, right? If one create a E field on this one, create a force on this one create E field on this, or a force on this, right? So you formulate some equation and then you go and solve for the unknown. Those of you from Polytechnic, please solve more of this kind of question. Because I think a lot of you are expecting I have numbers to put in the formula, get some numeric value. But a lot of times you have to leave them as a formula, as some symbol, and then do some ratioing or some simultaneous equation to solve, which is very familiar to people who come from A-level background. So if you're from Poly, just do more of this kind. Yeah, leave them as symbols and then eventually solve by simultaneous equation. Okay, so let's go to another topic. Ohm's law average. I don't think we have any Ohm's law question. Okay, so here's one. Hmm?
We don't have the also question.
There is.
Okay.
There is either direct or indirect. Yeah. Often is related to the current density or current. Yeah. So there are questions of this type. The potential difference between two opposing phases of a conducting cube with the side of 4 meters is 7 volts. So you visualize a cube. That means in its cross-sectional area is a square, right? With 4 meters by 4 meters. So 16 square meters in cross-sectional area. And then it runs some length, right? The voltage difference between the two upper and lower phase is 7 volts. So this is due to some current flowing and the resistance, right? Result is V equal to 7 volts, right? You're given the current density is 6.7 amp per meter square. So from the current density, you can calculate the current passing through that cross-sectional area. And you can calculate, you can calculate the resistance now, right? Because V equal to IR. So once you know the resistance, you can then calculate the resistivity, which indirectly is the conductivity. All okay with that? Next one. Electric potential in a medium with permittivity is 3.4 epsilon naught. In other words, the epsilon R value is 3.4, right? So the potential, electric potential is given as the equation V equal to 13 x to the power 4, y to the power 5, z squared, volts. That V is unit volts. So the voltage, which electric potential is dependent on the X, Y, and Z value. Find the volume charge density rho V in the medium at that point of X equal to -2, Y equal to 1, Z equal to 5. Okay, so which formula immediately come to your head that gives you volume charge density? Divergence of T. Divergence of T is rho V. So you need to calculate divergence of T. So del is a vector, right? Del x ax plus del y ay plus del z az, right? D, how to calculate D in this question? D equal to epsilon E. E equal to negative gradient V. V is given, which you can then differentiate, right? Find the gradient vector, right? For the negative, that's your E, right? Evaluate at this point. So you will have your E value at that point. And then multiply by epsilon, which is epsilon naught, epsilon r, right? Then you have a D. Good? Okay. Next topic. Electric field intensity average. You want to take a look? Okay. Given two charge, Q1 8 millicoulomb located at 410 in XYZ, Q2 -3 millicoulomb at -3, 1, -2. What is the electric field intensity at this point? Is electric field intensity a scalar or a vector? Scalar or vector? Electric field intensity. I share with you the English word. I don't know. Somehow my mind also, whenever I hear the word intensity, I think of scalar. But no, in the context of your course, intensity means vector. Okay. Never mind. Okay, just stick to your head. Okay. Whenever they ask you electric field intensity or magnetic field intensity, it means vector. Okay, so you expect your answer to be scalar part plus some unit vector part. That's why your answer here, that's the unit vectors, you see, ax, y, z. Maybe that's the difference between strength and intensity. Anyway, that's my consolation. Okay, just remember that. I've seen some question actually in the quiz just like that, asking you electric field intensity, is it vector or scalar? Yeah. Okay, this one should be easy, huh? Just apply superposition, right? Two E vector add together. Okay, so this one, something like that again, but this time leave them in some formula and solve, right? Because you are given E, Q2, and D. So you need to do some formulation and solve for simultaneous equation. Nothing magical from the previous one, similar. Just need to form this formula and then do some simultaneous equation to solve. Just bear that in mind. There may be quite a number of questions like that. You have to do this kind of formulation in equation, and then either solve them by simultaneous equation or just do some ratioing, divide one by the other and cancel off that as common. Okay, to move on. Okay, let's look at some other topic. Biot-Savart's law. There's only one question here, I think. You're given this 4 wires. You are told that the current passing through is 7 ampere. Find the magnetic field intensity. Yeah, so again, it's a vector at the center of this loop. Yeah, where the x value is 5, y value is 2, z value is 0. So since it's a vector, can you tell me the direction of that vector, that magnetic field at the center? What's the direction? Outwards. Okay, so it's AZ, right? Positive AZ or negative AZ? Positive AZ, right? Okay, so that's the direction. And how do you get the scalar part, the magnitude part? You're given this hint, right? Kind of difficult to see. Yeah, you're given this IL. L is the length of the wire. 2 pi r. R is, I think, is the radial distance from that wire. So you can just apply it now since these 2 wires same length. So you just multiply by 2. These 2 wires same length, multiply by 2. You have the length. Okay, I think I'll stop here. Any questions, anyone? Oh, by the way, so in addition to this, the other you must go through is all this lesson review type. There are some questions that are like the lesson review type also.
Lesson review.
Yeah, those are the bottom.
Please.
Yes, there are. There are some star like that, star after those. You notice the earlier one are more calculations. So although, if I remember correctly, you're going to choose your answer A, B, C, D, E. Nevertheless, it's calculation, You calculate, then you choose from there. So at least it helps you. If you can't find any of those answers, likely maybe you calculate wrongly. Yeah. Yeah, obviously you need to calculate. A lot of the questions require you to calculate, then choose from the answer. Yeah. Off my head, I think the entry is basically you tick one of the A, B, C, D. Yeah. So, yeah. Just off my head. Yeah. But nevertheless, like I said, don't treat it to say that it's MCQ and just do hantam. Depend on what, no such thing. You need to know how to calculate. Okay, I stop here. Those of you who have not signed the attendance, please sign your attendance. And I'm going to display what I have recorded for those online. If your name is not there, please alert me. These are the names I've captured. So type in the chat if your name is not there.
What? Fuzz.
Very. Oh, very.
Okay, thank you. See you all next week.